Okay, so let's begin. It is my great pleasure to introduce Emmett Witchel, who is a professor in the University of Texas in Austin. Emmett is a hardcore ASPLOS researcher, working on exactly what you want: operating systems, computer architecture, and the interface between them. Most recently on topics including CXL, memory, serverless computing, and trusted execution environments. The number of times that Emmett served in the ASPLOS program committee is in the double digits. Thank you, Emmett. Including as a program chair in 2019. Emmett's publishing recognition includes Best Paper Awards from SOSP, OSDI, and also Microtop Picks. And finally, Emmett is an ACM fellow. So,
thank you. Thanks very much, Dan. Yeah, I'm Emmett Witchel from UT Austin. I'm here to talk about CXL memory, joint work with a lot of great people, and let's get into it. So I'm starting my talk with something that hopefully you'll all recognize. I'm telling you a story. Once upon a time, I think human beings are hardwired to be interested in stories, to try to understand stories. So I'm going to tell you several of them today. Maybe I should start with something that's a little more culturally relative to myself. In the beginning, I think that's a pretty good way to start a story. We could also talk about a technical story. So this is Intel in 2015. I'm going to show you a couple of stories with this picture. I'll explain the picture at the end. But what Intel did in 2015 was they gave us SGX. These are protected enclaves. And what they said is, hey, there might be a region of your user address space that you want to protect in order to create secure software. And we think that we want to give you that fine-grained ability to protect yourself. Well, even before the hardware was out, some researchers at Microsoft said, this sounds great. Let's take this mechanism, throw in some legacy apps, and while we're at it, we'll put an entire library operating system in there also. So this being 2024, I wanted to visualize what Haven, a protected execution environment, actually looks like. So I took a bunch of the Haven paper, I gave it to AI, and this is what they came up with. This is actually quite a peaceable image. I see this as a nice protected haven for my computations. But back to the story, while people were putting all this code into enclaves, they also then realized this is not so good for security because we need to be careful about how much code is in there for our trusted computing base. So there was a whole bunch of work trying to eliminate some of that code to try to pare it down so that it could be more secure. And of course, this story maybe ends very recently when Intel made trusted domain extensions where they said, you know what, here's a facility to secure your entire virtual machine, because they saw that the granularity of protecting just part of your address space wasn't working for programmers. They said it might not be the best idea for security, but maybe for usability, we should allow you to protect an entire virtual machine. And if you do have code that you need to keep away from prying eyes, Intel has you covered. Here's another story ripped straight from the pages of our own ASPLOS proceedings. And it starts in 2000 with Horde, which did scalable memory allocation. Wonderful. 4 years later at PLDI, we had a lock-free version of Horde. That was great. So I took a bunch of the Horde paper, I fed it to AI, and it gave us this very explanatory looking poster, although I personally can't understand it. Of course, the words don't really make any sense, and maybe the ideas don't either, but Horde made a lot of sense to Apple, because Apple took it in 2008, they adopted it, and they even cited the ASPLOS paper in the code. So you might think that that's the end of the story, as I did. However, Emery Berger, the author of Horde, insists the end came when machine learning entered the scene recently for a memory allocator called Llama that used machine learning to reduce fragmentation. And of course, when you feed Llama and the text from that paper into an AI image generator, you still get the same explanatory square, but this time you have a nice llama on top as well. All right, one last technical story. Let's talk about Spectre and Meltdown. These are the microarchitectural side channels that we all knew about theoretically for a long time, but we didn't realize they were actually exploitable until 2018. And this really turned some heads. People got very concerned. The community really responded quickly. You had KPTI in Linux, where you had double the page tables. You had a page table for the kernel. You had a page table for the user. Intel responded with a firmware patch. So the community was on this problem. And here we have a representation for microarchitectural side channels that I just love, because it's an empty chair. And then behind the chair is a plant with what I feel like looks like a gorilla hiding behind it. So what better way to represent microarchitectural side channels, but a gorilla that you can't really see? Unfortunately, the end is nowhere in sight for microarchitectural side channels. We've had Foreshadow. Recently, there's a system, Augury. There's also a system called GoFetch. These work on data-dependent prefetchers. These are elements that are used in Apple silicon that allow you to steal secrets. And where is this all ending? I don't know. I think when these exploits first came out, there was some hope that we could quickly dispatch them. That has not been the case. It also hasn't been the case that there have been huge numbers of compromises, although from what I understand, there's now a Spectre v2 exploit in the wild that was just discovered this month. I believe the mitigation is fairly straightforward, but what does the future hold? How are we going to resolve microarchitectural side channels? This is a question I can't answer. However, if you do want to secure your data memory dependent prefetcher, so that's a prefetcher that reads data, well, AI has you covered for that. All right, so the image that I've been using during all these stories is this pyramid, which comes from Gustav Freytag's work from the mid-1800s. So that's a fairly long ago reference for ASPLOS. And what he noticed is that there's a similarity in the way stories are structured. So usually you have some protagonist who's just living their life according to a certain set of beliefs. So you have Luke Skywalker and he's on his farm, no problem. Then you've got an inciting incident and something happens and the protagonist can no longer continue living the way that they did. In this case, the Empire destroys the farm, kills the uncle. He's got to do something. So then you have rising action. He falls in with the resistance. He learns about the Force. He gains a mentor. All of these things are great. Eventually, we finally have the big climax where all the plot points come together. He destroys the Death Star, and you have falling action. Everybody gets awards, I guess, except Chewbacca. And then you have the denouement, which when I learned about it, is sometimes described as a little bit of extra spice that happens at the end of a story. My personal favorite example is from the Avengers. I think it was a cut scene, but after the huge cosmic battle, you see them tired and eating shawarma in a half-destroyed shawarma restaurant, and it's really a great contrast. But the reason I'm bringing this up is because I think metacognition is a worthwhile activity. So just like metadata is data about data, metacognition is thinking about thinking. And as researchers, I think we can use this to our advantage. Sometimes this kind of thing can get you out of a rut, and it can provide a certain amount of perspective, even though, of course, there's no crystal ball. We still have difficulty in understanding and seeing the future. However, if you take a look at this pattern, I think you'll see it in a lot of different research areas. So sometimes there's a piece of hardware or software or an algorithm that comes out and it opens a field. And then there's some foundational work in this area where certain basic approaches to a problem are explored, like distributed hash tables. There were certain algorithms. That's the foundational work. There's then often a long tail of problems. Some of these problems were known from the beginning and maybe were kicked down the road because there were other issues more pressing to solve. Sometimes these issues come up when you try to adopt a technology and it doesn't work in the field. And then finally, we end up deploying our technology and moving on. And this is where a certain area gets closed by the research community. So the reason I show all of these sort of quadrants to you at once is because some people, I think, tend to believe that unless you're writing a paper that's opening a field, you're not doing great work. And that's not the way I think. I think you can do great work in any of these areas, but it's nice to know what area you're working in. It's nice to know what area you're contributing to. It's also nice to know what area a paper you're reading or reviewing is contributing to. If someone is trying to solve a long tail of problems, you shouldn't criticize them for not being sufficiently novel, for not opening the field. So let's talk a little bit about Compute Express Linked Memory, CXL memory, and I'll give some more details and more schematics for those of you who are not totally familiar with this technology, but I do want to just talk about a couple of things. We're in the beginning of this technology cycle, so we're living our lives when memory became a limiting resource in a way that I'm going to explain in a slide. And our inciting incident is that a bunch of industry got together and standardized a way for hosts to talk to an external memory across the PCIe bus. And now we've had some of the foundational work that's been done. The best paper from ASPLOS last year, Pond, some of the authors are in the crowd. Also TPP from Meta is some of the initial work in this area that indicates that CXL memory has a bright future. Now, where exactly are we heading? Where is the climax? Will this make a difference? I don't know, but I'm excited about it. And I think that we can learn some lessons, and those lessons can be valuable no matter the ultimate technological fate of CXL memory. So here's an outline for the technical section of the talk. So I am going to talk about CXL memory, which I characterize as a technology that's primarily about cost savings, and it's primarily about disaggregation in the data center. And then I'm going to talk about my own perspective on CXL, a little sort of organization I call CXL pods that's really for increasing performance. And this is not really an original idea. There was a paper in last year's SOSP which used this kind of hardware assumptions. But under this set of assumptions, CXL memory is explicitly controlled by the programmer. And then I'm going to talk about some of the challenges that might exist for CXL pods. And in particular, I'm going to talk about tolerating partial failures, why you have to tolerate partial failures, why I think you should, and how we could go about doing it. So let's start with the basics. What's a computer? Let's go back to the 50s, and von Neumann told us that there's an organ called memory to keep track of in-progress computation. And here we have an exploded view of a server, and we've got some storage, we've got some cooling, we've got some compute, and up here we have our memory chips. And those memory chips need to physically be close to the processor because they're connected by a high-speed bus. And so what the Pond authors noticed, now we're moving to last year, is that there's a problem, there's a tension between the physical organization of your computer and the way you want to sell it in a virtual machine to your clients. If you sell all of the CPUs in a rack, you end up with a bunch of DRAM. Up to 25% of that DRAM is stranded and can't be sold. And this is an expensive resource, with the DRAM possibly costing up to 50% of the cost of the system. And so we don't want to strand this much expensive resource due to the physical organization. What we want is a way to flexibly carve up our physical resources and sell them as virtual machines. So that's the dream of disaggregation. With disaggregation, you have a cloud of compute, lots of processors, GPUs, doesn't matter. And then you've got memory and storage, and it's as plentiful as money will buy. How much capacity? How much money have you got? How much bandwidth? How much money have you got? But as the song goes, you can't buy everything. And in this case, you can't buy latency thanks to the speed of light. And so there is still some physical limitations that we would have to engineer around. But fundamentally, I think this vision is about optimizing for cost savings. It's about flexible partitioning of resources in a way that is transparent to applications. So this is the vision for what computing systems should look like. What's the ugly reality? The ugly reality, of course, is this wide and long hierarchy of storage where you have very fast, very small memory at the top, and you have large and slow memory at the bottom, and then you have system software to tie it all together. I mean, hey, this is what virtual memory was invented for, so can't we do the same thing now with some additional layers like CXL memory, which provides a nice, fairly fast latency, fairly high bandwidth, especially compared to persistent memory. And it turns out this works pretty well, as shown by Pond, TPP, and related work. Of course, this brings up a whole bunch of issues. Do we have enough layers? Do we have enough bandwidth at each layer? What about the latency? How accurate is our prediction? All of these issues, I think, are great. I think we're going to see a bunch of work of this in the coming years. It's awesome, but it's not what I'm interested in when I talk about CXL memory. So what I want to talk about is single host software versus a distributed system. So in a single host software, you have shared mutable state. Any thread can access any piece of state in your computation, and that gives you an incredible amount of power and an incredible amount of flexibility. So what you see then is a variety of efficient algorithms. This is a wonderful environment for software. Unfortunately, the price you pay is limited concurrency and limited scaling. So the kind of exemplar we normally think of in this area is a database. It's a great piece of software with really strong semantics, but it's hard to make it scalable. And on the other side, we have a distributed system where we have many hosts. And there, you really don't have so much of a choice for algorithms. If you want it to be correct, you need a replicated state machine. On the other hand, you do get scalability. Specifically, you get scale out, which means if your workload has a lot of independent work, it's really easy to absorb that work by just adding more compute resources. You also get some other benefits like fast failover, because once you've dedicated 40, 100 machines, what's one more for a hot spare? Unfortunately, I think we've been sold a bill of goods, especially in the research community. I think we underestimate how difficult it is to construct and maintain and performance tune these distributed systems. We're too smart. We hang out with other researchers who are too smart, who are always telling us it's not that bad to build a distributed system. It's not that bad to figure these things out. But if you look at the top 5 companies, they've got lots of PhDs who are performance tuning these distributed systems, but it's difficult to bring this benefit to everybody. So the question, oh yeah, so if I want to draw an analogy, over here on the single host side, it's sort of like the tropics. Right? It's a very welcoming and environment for a variety of life. We have a colorful macaw. And for distributed systems, it's a brutal environment. It's difficult to survive. And polar bears, you might think are cuddly, but they're really vicious. So what can we do that might be in the middle? Can we get a CXL pod, which would be a bunch of different machines, physical machines, connected to a CXL memory module? And is there some temperate climate we could achieve? It shows a white-tailed deer. It's a little bit arbitrary. But the idea behind the CXL pod is that we can get a lot of the benefits of the software infrastructure of the single host system. There is going to be a fair amount of synchronization and issues around that. I'm going to talk about that in this talk, but hopefully we can encapsulate that complexity within data structures. And what we have is an efficient system with low tail latency. And the vision here is kind of like the SQLite of distributed systems. So I bring that up because traditionally, there's nothing harder to install and performance tune than a database. It manages a whole bunch of hardware. It's really difficult to get right. And yet SQLite came in and said, let's go the opposite route. We're going to throw out all the complexity of a normal database. We're not even going to give you concurrent access, and we're going to set up on top of a file system, which makes this really, really easy. And what happened is that you've now got hundreds, if not 1,000 SQLite databases on your phone. They manage your contacts. They manage your media, because it's a really powerful environment for software to get access to structured data. And that's what's important. And it has helped bringing that to phones has helped the phone environment flourish. So here's the long promised schematic of what we're looking at for a CXL pod. So there are a couple of things to notice. The first is that we are running a single application. And this is, think of a single node piece of software that you have had to port, but the porting effort is light. There are physically distinct hosts, each running a separate operating system. Then there are processes. These processes have multiple threads. These threads have access to local DRAM. And then there is a physical connection between each host and this CXL memory module, which exists independent from the hosts. So in order to realize this vision, we're going to have fine-grained sharing of CXL memory on cache line granularity. And I am careful to point out that this functionality has been specified. It's in the 3.1 CXL standard. However, so far as I know, there are no hardware prototypes, and it might be difficult to achieve. If we can achieve it, we are also going to need some support from our system software, from the operating system, from the memory allocator. But let's take a look at the scope of what we can get in one of these CXL pods. So think of a pod as having 16 hosts, so half a rack. Maybe eventually we'll get to a rack, but half a rack seems reasonable. Certainly the pod authors thought so. The pond authors thought so. And then let's take Intel's recently announced Sierra Forest processor. It's got 288 cores, they're E-cores, they're not performance cores, but it does have 288 cores. That's 4,500 cores in a single CXL pod sharing memory. So I went back to the MapReduce paper from 2004, one of the poster children for a distributed system. And if you look at that paper, they ran on 7,000 cores. And in fact, it wasn't even cores, those are hyperthreads. So it's really more like 3,500 cores. So this looks a lot like a distributed system in a box, in a sense. So what will we run on a CXL pod? So the one clear idea is an in-memory database. An in-memory database has high performance requirements. It has high availability requirements. And fundamentally, the bet I'm making, or the bet that I think is interesting, is that coordination by shared memory is more efficient than the alternative. And what is the alternative for an in-memory database? You have to partition your state. You put some state on one host, you put other state on another host. And then if there's any transaction or data processing that has to involve data across those hosts, you have a distributed transaction protocol and you communicate over the network. So here our birds have our partition state and they're communicating via letters. Another possibility for a CXL pod is a long-running computation that has lots of state. Think about training a lot of machine learning models. You have a computation that's valuable enough to require fault tolerance, but checkpointing this state is slow, consumes a lot of storage bandwidth, and so you'd rather do it using CXL memory. So what are the requirements for a CXL pod? Well, as I said, one thing is this fine-grained access to memory, but also the most efficient way we could use a CXL pod is if we got hardware cache coherence across the entire CXL physical memory space. Can we get this? We don't know. It's uncertain at this time. There are some technical challenges to doing this. We might get it. We might only get hardware cache coherence across part of the physical memory space. It might be a limited form of hardware cache coherence. It might raise the cost of the CXL module. Be certainly interested in talking about these possibilities with you. But the underlying question here, and it's a question that we often see in ASPLOS, is what should the hardware be providing for software? So I started this talk telling you about enclaves, which is this way to protect a little bit of your address space. And that was a really neat primitive, but it turned out to be pretty hard for software to use. But fortunately, this is one case where I think software's needs are clear and hardware can provide a really powerful primitive. So the example I'm going to take a look at in order to explain something about CXL memory is a previous memory technology, persistent memory. And if you wanted to write persistent code that accessed persistent memory, Intel told you to do this before 2016. We're storing a constant into a memory location. Then we kick that memory location out of our cache. Well, our processor knows about that instruction, but of course, the external world doesn't necessarily know about that instruction, like the memory controller. So we need an S fence, a store fence, which makes sure that this cache line is visible to the external world, like the memory controller. But then, even though our data is now in the memory system, the problem is that there might not be enough energy to make it persistent before you have, if you have a catastrophic power failure. So you need an additional instruction, the pcommit instruction, and that instruction also needs to be visible to the external world before you can be sure that your data is persistent. Well, unsurprisingly, people who wrote software found this awkward, it was slow, and so Intel listened, and after 2016, the pcommit was deprecated. So we were able to get rid of that instruction, we were able to get rid of one S fence, great job. And in fact, in 2020, we got EADR, which eliminated the need to do cache flushing. So now what the hardware is doing is it's saying it's got sufficient energy to get that data out of the cache and into the memory system to be globally visible no matter what happens. And that's really useful for software. This is an example where hardware, even though it's difficult, can provide something that's directly usable to reducing the complexity and increasing the efficiency of software. There is no EADR for CXL memory, but there is an analogous feature called global persistent flush, which we hope will be provided. So let's talk about some of the challenges. There's all this opportunity. In particular, I do want to talk about partial failure. So what do I mean by partial failure? Well, I have what sort of looks like a distributed system. I have multiple hosts. They're computing. I have multiple processes. What happens if one process dies or one host reboots? Do I have to reboot or restart the entire system? Tolerating partial failure means that the application can remain available while one part of it dies and recovers. So your OS can reboot while the other OSs continue to process requests and do normal operating system things. The question of how we deal with this in a CXL pod goes to the heart of what is the fault model. Is it like a shared memory multiprocessor, where if anything goes wrong, you just have to reboot it? Or is it like a distributed system? Well, because it has multiple operating systems, I think it looks more like a distributed system, and a distributed system should tolerate partial failures. So what can go wrong on a partial failure? What am I worried about? Well, up here, I've got a picture of a thread failure, which if you can see it is pretty gnarly. But the problem for computing systems is that our shared data structures will go into this shared CXL memory. So we have things in here, queues, trees, and in order to access them, we need to synchronize. And if you take a look at how operating systems and applications synchronize for shared data structures, the situation isn't good in the sense that they use efficient primitives like spin locks, semaphores, but these primitives are not fault tolerant. If your operating system grabs a lock and then reboots while holding that lock, your system will deadlock. A further problem with partial failures is that it means that OS reboot is no longer a global quiescent point. And this is a trick that was used in a lot of persistent memory systems where they noticed, hey, I've got this persistent memory device. It's being controlled by a single operating system. What that means is that when the operating system reboots, this is a great time to do housekeeping. I can do garbage collection. I can rebuild all of my indices. It's great, but it won't work on a CXL pod because while your operating system is rebooting, some other operating system and user processes are still computing. So on recovery, we need to get our state from somewhere. Where are we going to get this trustworthy state? Because storage is slow and has limited bandwidth. So my suggestion, let's make the CXL memory persistent. And what I mean by this for this technology is to give it an independent power supply so it's in a different failure domain. We will also protect the integrity of the memory contents using error correcting codes. And this can have consequences. It can raise the cost of the module, hopefully a moderate amount, just as ECC is a moderate cost. But if we do this to protect the CXL memory state, that means that on a partial failure, we can restore from CXL memory. Our applications can remain available during recovery. And we have this wonderful low latency, high bandwidth storage device where we can do logging and we can play lots of great software tricks with great efficiency. So persistent CXL memory gets us out of some problems, but of course, we still have the problem of synchronization and synchronization under partial failures. So how are we going to address that? Well, if you hear, I've got a problem with synchronization and failure, I hope you think of transactions. Transactions are a wonderful primitive. They are fault tolerant. They're used in persistent memory systems to do memory allocation. And I'm just going to walk you through a particular example here because I think it's fun. So here I've got some code where I'm getting a memory block from my persistent memory allocator. And then I need to store this pointer as a persistent root. And what that does is it registers it in a namespace such that when I recover, I can get access to that pointer. Well, I hope you see a problem here. if I get the pointer from the persistent memory allocator and then I crash, I now have a persistent memory leak. There's no way for me to get access to this data anymore because it's not registered as a persistent root. And the persistent memory systems noticed this problem, and so they added a transactional API to do memory allocation. And that was great, but unfortunately, tolerating partial failures is a more pervasive problem than memory allocation, and I would like to avoid mandating a fully transactional programming model. As much as I love transactions, I don't like to force things on people, and I'd like to see if we can find a more efficient special case solution. So if you're looking for correctness in the face of concurrency, of course, we arrive at linearizability. So linearizability was invented in 1990. On a personal note, I entered grad school in 1995. I printed out the linearizability paper and I carried it around for a year. And I used to take that thing out and read it and try to understand it. And to be honest, I never did. It was only when the material appeared in follow-on work that I was able to understand it. But let me give it a shot in terms of trying to explain it to you here today. So we have a queue, which is just some object that has a certain semantics that we understand the sequential semantics for, but we want to adapt that to a concurrent setting. So we have many clients that are accessing our queue. So how does a client access the queue? They do operations like enqueue and dequeue. So they contact the queue saying, hey, I would like to enqueue this object. That's the invocation. And the queue gives a response, which says, I've got your object. Or you do an dequeue, and here's the object in your response. Linearizability says we can choose a linearization point in between the invocation and response such that if we reorder all operations to be sequential with respect to that linearization point, that sequential history is correct for a sequential specification of the object, whether it be a queue or a tree. So I hope that was enlightening to you. If it's not, please check out the Art of Multiprocessor Programming, Herlihy and Shavid, who I think explain it better. Unfortunately, linearizability, as useful as it is, doesn't say anything about failures. And so we had durable linearizability in 2016, and it turns out that durable linearizability had some problems for partial failures, so we got detectable execution in 2018. So here's the problem that detectable execution solves, at least in a rough and ready intuitive way. The problem is that a lot of applications need to execute operations exactly once. So if I crash while I am enqueuing an object into a queue, on recovery, I need to know whether that enqueue succeeded. Well, you might say, just take a look at the state of the queue. But I can't because this is a partial failure. While I failed, there were threads that were live that were still processing things. They might have dequeued that object. So I don't know whether I was successful or not. And so I need to save enough breadcrumbs such that when I do recovery, I can know whether the operation that was in progress when I crashed actually succeeded. So for correctness conditions under partial failure, for these kinds of systems, I think we're going to need linearizability and detectable execution. Okay, I wish I could talk about some of the systems I've built in this area. Unfortunately, I can't, but I have to show you at least one graph or one measured result. So please bear with me. This is the result of an OpenMPI broadcast micro benchmark. So we're just taking values and broadcasting them to all of the machines in the system. In this case, I've got 16 virtual machines. This is a message passing benchmark. It is a distributed systems benchmark, which might be a little bit funny because I keep talking about CXL as a way to have a single node to run single node software. But the point of this experiment I'm trying to get across to you is to validate this assumption that memory is more efficient than communicating with network messages. So I've got two different message sizes, small and large. And in both of these cases, relative to OpenMPI, using CXL as a transport instead of using the network is faster both for median latency and also for tail latency for both small messages and for larger messages. So I think there's a lot of promise to this technology, and there are a lot of systems building to be done. That said, I do want to transition out of the technical section of the talk, and I want to talk about the problem for CXL and also the problem, the promise in general for computer science research. So I think one of the things to notice from some of the information I've already presented, we got linearizability in 1990, but it took 30 years to get durable linearizability. So why is that? Well, it turns out that I think the world of mathematics is very complicated. There are so many problems out there, and we get lulled into this sense that all the important ones have been solved. But I think that really is a misperception. In fact, technology and the progress of our problems helps identify what areas of theory and mathematics are worth mining for the kinds of systems that we build. I also return to this problem of what should hardware provide for software. Now, sometimes this has an easy answer. Do I want encryption? Yes, I want encryption. Do I want hashing? Yes, I want hardware hashing. Give me a video decoder. That stuff's easy. But one of the things that's exciting about CXL memory is that it makes certain distributed systems problems, like failure detection, really easy. And that fundamentally changes the software programming model in a way that I think can have more profound ramifications than a simple accelerator. So what are we trying to learn? Even if CXL fails, if we understand the systems that we've built, if we understand how they work, we can break down these solutions and use those pieces as parts of the new systems that we want to build. Why do we do research at all? I think it's a reasonable question. There are a lot of answers to this. Of course, we want to find things out. One thing I want to put up here is ego gratification. Okay? I'm having a great time talking to all of you. I hope there are students out there who come to ASPLOS and think, you know what? I think my work deserves to be shown to this community. I'm going to work harder. I'm going to get up there. If you ever are interested in the work of Carl Jung, a great psychologist, he talks about the shadow. Just because you have selfish or greedy impulses as a motivation doesn't necessarily mean the results of that are bad actions. Oh, but sorry, there is one word when we are talking about research that everybody loves to use. I think we all know what that word is, and I just showed it to you, but that word is impact. So when it comes to research, there is no ceiling on the importance of impact. We all want to change the world. We all want to have a positive effect on other people and society. And so if you work in industry, I hope they tell you that if you have one impact, you should have 3 impacts. You should have a large impact. You should have a dangerous amount of impact, and ideally a catastrophic amount of impact from your research. So look, I like impact. I think it's great, but it's not actually why I do research. I like the aha moments. I like pursuing truth. That's why I'm in this game. If you take a look at Google and ask it, what is a PhD? It tells you it's an academic degree that pushes the boundary of human knowledge in a specialized field through focused research for several years. I think that's a pretty good definition, and nowhere in there is impact mentioned at all. On the other hand, if you are interested in insights, if you are interested in pursuing ideas, insight can be remarkably hard to find. It can be even hard to search for, and it can be hard to recognize. So one of the examples I like to give is I went to graduate school at MIT, which is in Boston. My family lived in New York, so I used to ride the bus from Boston to New York. And I can't tell you how many times I got on the bus and I was thinking about my research life and I thought, I've got it. This insight is what's going to get me a PhD. And man, I was wrong 100% of the time. Not only did none of that get me a PhD, I can't actually remember when I started thinking about Mondrian memory protection. I was on a bus, actually from a train from New York to Boston, and I was sketching out a data structure for hardware to keep track of fine-grained software memory objects. That's my first memory of working on my thesis, and I can't even remember exactly why I was doing it. The nature of insight is that it's fleeting and it is difficult to achieve. However, popular culture gives us a key. It tells us that if you are looking for insight, you need to write on a window. And so the PC chair for your next ASPLOS, Chris Rossbach, I know when he worked at Microsoft, he had equations written on his window because he knew that meant he would do good research. I think the problem here, in part, is we often overvalue the individual and undervalue the group. Research is a social activity. It happens within the context of a research group, your peers you interact with every day, and that's the important context. There's also a larger context, this research community, where we come together and we love to talk about great ideas. What are you pursuing? How can you make sense of the world? How can you make sense of the things that are happening in our world and in our technology? These are vital to the process. The whole really is greater than the sum of its parts. I can only write the papers that I do because I learned so much from writing them, which sounds kind of weird because when I'm not writing papers, I mean, I am teaching classes and doing other things, but I'm still thinking about research. But it's still that process of the paper push where I don't necessarily recommend it for you, but for me, maybe involves a certain unreasonable level of effort. That effort, when combined in a group, really lets you achieve amazing things. I had a colleague, Scott Devine, who's a founder of VMware, and he told me that he knew he was in the zone when he was writing a paper, when he would walk across campus and have totally nonsensical thoughts like that person is in the wrong hash bucket. And I think what's happening is we only have so much brain. And when you try to pour every last drop of a certain problem into your brain, it pushes out the normal functionings that your brain is normally responsible for. But this is actually a good thing. It gets you to that level along with talking with other people, thinking about a problem nonstop. You can achieve a level of insight that you can't achieve in any other way. It's sort of like synesthesia. You've heard about it. Musicians often describe not only hearing music, but also being able to see it and visualize it, in part because they're using so much of their brain to process that information. So if you're starting your research career, what should it look like and how do you remain happy over the long haul? So the first thing I'll say is the most trite platitude I can think of: study what you love. I will temper that by saying also what you're good at, because that counts too. If I am going to give that advice, I have to at least show you this quotation from The Goldfinch, which is probably my favorite book ever. So you can read the quote. You should definitely read the book. But remain open. Think about working on different problems. So my entire career, I've said things like, I will never work on topic X, and then I have found myself working on topic X. And I think that's a wonderful thing. I think it's important to have strong opinions, but it's also important to revisit them and to evolve in your thinking. The other thing to notice, though, is that topics recur in popularity. So when I graduated, I had a thesis in hardware assisted memory protection. But at the time, everybody was talking about software memory protection. It was all about the common language runtime. It was all about managed languages. Nobody really cared about hardware memory protection. Well, times change, issues come back. I've also always been fascinated by low-level software that controls hardware. I don't really know why. It just always gets me interested. And so what I had to do is find the right fit between my research interests and the research interests of my community. And also for those of you who are looking for jobs, you need to find the right fit between your research interests, your research style, and where you want to go. I know, I think that I was denied a certain faculty job because I was not core operating systems, but I got the job that I wanted because I bridged operating systems and architecture. It's not a matter of seeing these problems as a rejection. You just need to fit your motivations into the context that you are in. So I'm almost done. I just want to conclude with a couple of observations. We've talked about how to make ourselves an even better research community. There was a discussion at the business meeting, for those of you who could power through to the very end, about the situation that ASPLOS finds itself in. It's a little bit a victim of its own success. And I think we all need to think hard about what to do. because the situation we're in is not sustainable. I personally don't like 3 annual deadlines. I'd like to go back to 1, maybe 2. What else are we going to do? Can we have the history of paper reviews from previous conferences? Is that a good thing? Is it bad? Should we have authors pay for submission in cash, in reviews, in blood? I don't know. Talk to me about it. Talk to the conference organizers about it. This is something that we need to solve as a community. And then finally, I just want to say something about ethics. I think the purpose of religion is to get us to recognize the humanity in each other. And religion, unfortunately, does not always succeed in that regard. But another thing that's good about religion is it gives you a framework for talking about ethics. And unfortunately, without that framework, it can sometimes be difficult to talk about ethics. So this is a quotation from a YouTuber I happen to like who does movie reviews. So it was in the context of a movie review, and he goes by the name like Stories of Old, but I just want to read this to you because I think it's a really beautiful sentiment. No matter what our place in life is, each human being possesses a fundamental inner freedom that cannot be compromised unless we let it. And that therefore imbues us with an innate demand for personal responsibility. I think that's a really wonderful sentiment. I think it provides a grounding for ethics that is non-religious, and I hope that it provides some inspiration and some basis for your actions. Of course, I have to thank my own research group and my wonderful collaborators for all of the help that they were able and all the insight they were allowed me access to. And I'd like to summarize the talk, but quite frankly, there's no better summary than this.
Great talk, Emmett. Mark Hill, Wisconsin, my PON co-authors. Thank you for the kind words. Just want to talk about the I like the idea of a pod. That's very good. What about hardware coherence, right? We can totally do it, right? It just takes a lot of state. So in the medium term, it's not going to happen in my judgment. So is it a showstopper if we have, 1% of your memory fully hardware coherent for synchronization? And for the rest of it, you have to flush, and also the reader has to invalidate. Is that a showstopper?
Yeah, I mean, it's a good question. I'm slightly disappointed that the number off the top of your head is 1%. I would hoping it would more be like 20%. Look, it can be done. If you take a look at the databases that we're looking at, as you say, only the actual memory consumed by your locks is not that, and your synchronization primitives in general, it's not that much. The problem is just, you've got to now reorganize your data structure. You potentially have to reorganize some of your algorithms because you've grabbed a particular lock, but you don't have access to the associated data. Is it a showstopper? No. Is it concerning? Yes. Right. Part of the I came of age in the 90s, and for me, what that means is software distributed memory. I hate. I feel like this is a system idea that will always fail. And what I like about CXL is that it's got hardware coherence. So I need some of it.
Chris Kozirek, Stanford University. Good morning, Emmett. Great talk. So CXL is great. It has a couple of very important use cases. One is it gets you more bandwidth per processor pin, and most chips are page front limited, so that's great. It allows you within a small neighborhood to exploit stranded memory for less frequently used data. Fantastic opportunity too. But let's talk a little bit about large-scale shared memory with cache coherence. It's a great research topic, but I wonder, what did we learn from the last time we tried this? So this is not the first time we did this. We built, SGI machines and SAN machines. And there was this observation that Luis Barroso put in the first version of his book. And he said, look, if somebody built a 128-node cache coherent system, if your app is exactly that size, it's great. If it's a little bit bigger, you still have to go distributed system. So you have all the distributed problems. You bought this express machine for no good reason at all. And if your app is smaller, you waste that machine. So they went back to two socket servers, and they built scale-out systems. And we told people to do microservices that do amazingly complicated stuff relatively easily. So what can we learn from that? And do we think that this time around, if we build this 128 node CXL shared memory cache coherent thing, something will work better, will magically some application and break this issue that Luis brought up?
Yeah, so that's also an excellent question. So, sort of scale and do you need an exact fit? And look, I think part of the problem or part of the issue is that the problems that people were working on at the time were really scale out problems. And if you have a scale out problem, a scale out solution is the right thing. The thing is, and what then you saw was this sort of real dip in the semantics of these systems. So we had scale out databases, but they had really bad semantics in terms of consistency models. We've recovered some of that, but given the size of problems today, I think a lot of problems can fit in a couple of thousand nodes. And given that the advanced state of virtual machines, if we can virtualize this, you can sell a virtual pod and you can size it to whatever you need for your particular problem, as long as it fits within a certain physical limit. Is this going to capture the world for a certain class of software? I think that it might.
Thank you.
Tanvir Ahmed Khan from Columbia. First of all, really great talk. I really like the way you actually introduced CXL. I hope to introduce my students like that as well. And also really insightful talk about research and how to do research as well. So my question is more about I would say, utility of CXL. So since we are also working on that, and I understand the latency benefits that it provides, but at the same time, just like you showed that the fault tolerance or the failure detection and failure recovery, when we have to provide those guarantees, the cost and complexity that brings in, do you think that will, again, for lack of a better word, don't you think that would outweigh the benefits or the utility that CXL will provide?
Yeah, no, and that's an absolutely legitimate question also. But yeah, so basically what you're asking is like, well, look, you're sort of selling me a bill of goods, right? You're saying, oh, just take your single node software, but you have to port it. And maybe the port is more difficult than you thought. And maybe there's a data structure in there, but that data structure is not scalable because you're using a single lock. You can make that lock recoverable, but that doesn't make it scalable. I do think that those are very valid concerns. What I hope, and it's a bet, is that we've developed enough technology for scalable data structures that we can use that to encapsulate a lot of this complexity in porting. Look, there is going to be some programmer effort. I view that a little bit as a feature rather than a bug. Whenever you're talking about maximizing performance, programmer effort is the best way to get that. So some of that is okay. Is it a crushing amount? That's the important question. And yeah, I'm putting my hope in scalable data structures.
Thank you so much for the talk, Mohammed Ismail, and I go to Virginia Tech. I really resonate with the last few slides. I defended my PhD a few days ago, and it's really great to see all that. But my question is on CXL. With the disaggregation and all of that happening, and there's a lot of endpoints that will happen. What is your take on the security issues and the security impact that you would need to have because of it? I know that CXL has a sort of memory encryption mechanism, but it's pretty coarse-grained. But what do you think about the security issues that may crop up because of the disaggregation?
Yeah, so that's also a good question. And, to be honest, I haven't thought about it, too much. I mean, so first of all, when it comes to security, you can mean different things, and you can talk about side channels, which of course are going to be hairy. But just on the basic level, I do think the operating system should be in charge of managing CXL. One of the things I sort of didn't talk about is my model is that all the operating systems are cooperative. And so they also all trust each other. Now, can we eventually get to the point where they don't have to trust each other? Maybe. That seems sort of complicated. But as long as you do have, some trustworthy system software, I do think you can at least build a system that's up to the current standards of security, even though that might not include side channels. And yes, if you've got multiple virtual pods on the same physical pod, what can they learn about each other? Those are good questions.
Thank you.
Yeah.
John Demme, Microsoft. You spoke about partial fault tolerance in terms of the compute nodes. What about partial fault tolerance in terms of the CXL memory system? Like you don't want, if part of it goes down, you don't want the entire CXL pod to fail because that's a rather large blast radius. Is that addressable in software? What hardware mechanisms do you need to deal with that?
Yeah, Yeah, so that is a great question, and we did, we sort of stumbled into this, and it turns out I had a very outdated notion of the reliability of DRAM. So I cited all these great studies from 2010, and then found the more recent studies, and the record is spotty, and that's why I had a slide on making CXL memory persistent. And what I mean by that is it does need to be in an independent power domain, because people are concerned about power failure. Now that doesn't, help you if your entire data center goes down. And then also ECC, the error correcting codes, there is compute, there's an external memory controller for the CXL memory. And in the specification, you can do heavier forms of error correction than you can do in a standard embedded memory controller. So I am sort of putting my faith in those hardware technologies. If we think it's important, I think we can build reliability into the memory, because that's one thing that I think hardware should be giving us.
Thank you.
Hi, I'm Sudarshan Kannan from Rutgers University. First of all, a great talk. I really like the use cases that you discussed. So let's assume that getting cache coherence is really hard and we don't kind of achieve that. So in that case, what's your view on still using virtual memory for CXL, like things like TLB invalidations, coherence, all those kind of things? Is it still needed, or with something like a pod abstraction, maybe that's time to kind of get rid of that in the CXL?
Yeah, I mean, and now you're asking a tough question that I don't have a full answer for. So yeah, so let's say that we can't get hardware cache coherence across the entire space. We needed at least some. So maybe we put our synchronization primitives in that area, and then you've got to deal with software coherence. And look, software coherence comes up a lot. It tends to work in GPU scratch pads because you just pull this data in and you read it a ton, and that's awesome. But anytime you're sort of updating, it tends to be a hassle. So look, I can try to say my stock line here is that we're going to hide this complexity in data structures. We're going to hide it in libraries. I hope we can. If we can't, we're doomed.
Yeah, because there's no one else. So then the question comes to point that is data sharing still kind of important in the era of CXL, or that's?
Well, yeah, or is data sharing important? And look, there's a certain leap of faith here that I am making, because if all of your problems are scale out, like you're done, you're set. Like, congratulations. One of the things that I sort of didn't talk about is there are these features on the web. I don't know how high performance they need to be, but things like time limited deals. You want to show people things that are relevant, that are personalized, that are relevant to their social circle. These things, I think, do require sort of unstructured access to data that becomes inefficient. But how important is this problem? I don't know. And I'm definitely looking. If you've got an application that needs this, let me know about it.
Thank you.
Yeah.
And this is why I knew you had